Okay, so this is a new video that I'm trying to do, a new series of videos that I'm going to try, where I go through and review material that you will likely be covering in your courses. I think this is a pretty good way to either watch this before your class so that you're caught up with what's going on, or something you can watch as like a refresher, maybe if you missed a day or not. Now, I want to get out of the way really quick that I didn't write this guideline or anything. I'm following Griffith's Introduction to Electrodynamics, the 4th edition. It's a great book. It's a book that basically every undergraduate is going to use. And that's why I'm using it. There's a lot of great problems that I've done out of this book that is on my channel. So sometimes I might refer to a problem, and it's a problem that I've already done. So it'll just be another resource for learning electrodynamics. So with that in mind, we're going to start with the first section of the first chapter, which is called Vector Algebra. So, and this is an example given in the book. This isn't my unique example, but if you imagine walking 4 miles north, stopping, and then walking 3 miles east, you could say, okay, well, I walked a total of 7 miles. 4 plus 3 is 7. But that's not how far you are from the origin. So how far you are from the origin is what we call our displacement. And hopefully you can recognize this is a 4, 3, 5 triangle. So you are a distance 5 miles from your origin. And that quantity is our displacement. Displacement. Not to be confused with the distance. Hopefully that's something that was discussed in earlier physics courses. So what we call things like displacement are vectors. And one way you can think about vectors is an object that has magnitude and direction. Now, this really isn't a rigorous definition, and I hope in a few videos we'll be able to talk about what vectors mean on a deeper level. And if you've taken some linear algebra, you might be somewhat more familiar with this and kind of have a better mathematical understanding of what vectors are. But it's a decent enough starting point. So vectors, just a few examples, would be velocity is a vector, acceleration is a vector, force is a vector, momentum, that's a vector. I need to start writing nicer, don't I? So these are our vectors. Hopefully you're familiar with those. And we also work with what's known as scalars. So scalars don't have direction. So we think of that as something with just some sort of quantity. So for example, mass, you could have a certain mass of something, but it doesn't really have direction. Charge is something we'll talk about in this series. That's a scalar quantity. So is density. So is temperature. So we have these different objects like vectors and scalars, and we're going to work on them quite a bit. One thing to know about vectors, scalars are kind of not too complicated. If you have a vector A, then the vector negative A, we sometimes refer to these as tips and tails. So basically your tips and tails, your endpoints, that might be a better way. Your initial point and your terminal point, they flip. So what was your terminal point is now your initial point, and what was your initial point is now your terminal point. So that's what the negative sign does to our vectors. Okay? All right, so now we need to talk a little bit about what we can do with vectors. Well, number one, you can just add vectors. You can just add vectors. And the way that you usually do this, if you have a vector A, vector A, and then you have a vector B, there's something called the tip-to-tail method. And essentially, you're going to take the initial point of B and put it at the terminal point of A. So start by doing that. So vector A, vector B, and then what you do is you connect the initial point of your first vector A with the terminal point of your second vector B. So this vector is vector A plus B. Okay. So that's kind of graphically how you do that. One cool thing to note about vector addition is that it is commutative. So vector A plus vector B is the exact same thing as vector B plus vector A. Okay. So you can kind of see, we did that over here. Say you have vector B, right? And then we want to put vector A to do something like this. This vector is B plus A. And, you know, you can't quite just judge by looking at it, but those are actually the same vectors there. Okay? Another thing you can do is it's associative. So vectors are associative. So vector A plus vector B, if we were to group that together and add a vector C, is the same thing as vector A plus, and then group together vector B plus C. Okay? And just like how we talked about the negative signs, one way you could think about it is if you have vector A minus another vector B, that's the same thing as vector A plus the negative vector B. So pretty straightforward if you're just adding two vectors. There's some multiplication we should talk about. So 2 is scalar multiplication. So let's just say alpha is a scalar. Okay, well, alpha, a scalar, times two vectors can be distributed just how you would imagine it would. So nothing groundbreaking here, just kind of laying the groundwork. And then the next thing we want to talk about is multiplying two vectors. And the first way we're going to do that is what's known as the dot product. Which the dot product, which you can kind of denote with that dot, is equal to the magnitude of vector A times the magnitude of vector B times cosine of the angle between them. So if you can imagine vector A, vector B, this is that angle theta that we're talking about. Okay? So that is our dot product. So that's one way you can multiply vectors and result in a scalar, because A is a scalar, B is a scalar, and cosine of theta is also a scalar. Now, just like before, when we were talking about adding vectors, multiplying vectors through a dot product is associative and commutative. So A dot B is equal to B dot A. And you can also, if you have vector A and you dot that with the addition of two vectors, you can distribute. So this is the same thing as A dot B plus A dot C. And I'm just going to note these. This is equation 1.1 and this is equation 1.2. So these are referenced in the book. Those are good to know. A few things to note about the dot product definition here, is know what happens when theta equals 0 degrees and theta equals pi over 2. So if cosine's 0, then the dot product is just the multiplication of the two vectors. And in that case, the vectors are parallel to each other. They're running parallel to each other. And at pi over 2, the two vectors are perpendicular at 90 degrees. In that case, the dot product is 0. So in a way, the dot product kind of tells you how in a line the two vectors are. Okay? So let's do example 1.1, where we define this vector C as vector A minus vector B. Okay? Now, we want to calculate the dot product of C dot C. Okay, well, C is A minus B, and we're dotting that with A minus B. Okay? And with what we know about dot products and our algebraic rules, we can distribute kind of like how you would expect. So A dot A is just going to be, well, I'll just write it all out. We have A dot A. Then we have minus A dot B minus B dot A plus B dot B. But remember that this is equivalent to A dot B. Okay? This is just A squared. And this is just B squared. So C dot C, which is just C squared, C squared is then equal to A squared plus B squared minus 2 times the dot product A dot B, which of course, A squared plus B squared minus 2 A times B times cosine theta, using our dot product definition. And this here is known as the law of cosines. So using with what we know about vectors, we're able to show that. There's one last type of vector operation that's worth talking about, and that is the cross product. So the cross product between two vectors, call it A and B, is the magnitude of A times the magnitude of B times sine of the angle between them, and then this is known as our normal vector, and it's a unit vector. So unit vectors have magnitude 1. So the unit vector, so if we take the vector n divided by the magnitude of n. Okay. And if you can imagine, let's just say you had something like this. In other words, this is like your y-axis, your x-axis. N is either going to come out of the board. Oop, not mean to do that. Can I undo that? N is normal or perpendicular to both vector A and vector B. So that means the only option, two options, is either the normal is going to come out of the board, like it's going towards you, or it's going to go into it, like it's going into your computer or whatever it is you're watching this on. Okay? So A cross B, the cross product of any two vectors, produces another vector that's mutually orthogonal or mutually perpendicular to both A and B. So one thing I brought up is, okay, well, there's two vectors that are perpendicular to both A and B. So which one is it? Well, we use what's known as the right-hand rule. So if you can imagine putting your fingers along vector A, your first vector, and then curl them in the direction of B, you kind of see that your thumb is going into your phone or your tablet or whatever it is you're watching this on. So that is the vector that we're talking about. Now, you might notice that if we did it backwards, if you do B cross A, well, now it's going the other way. Now it's coming out of the tablet or out of your phone or whatever it is. And that's because the cross product is not commutative. In fact, it's anti-commutative. So the vector B cross A is equal to negative vector A cross B. Okay. Another property about the cross product is it's distributive. So if you cross vector A with the addition of two vectors, it basically works how you think it would. You do A cross B plus A cross C. And we'll just label a couple of these. So this is 1.4. This is 1.5. And I'll just make note, 1.3. This is for the, I didn't specifically write it out, but if you dot two vectors that are the same, so A dot A is equal to just the magnitude of A squared. And that's equation 1.3. Okay, so that's most of what we need to talk about, but it's also helpful to understand what the magnitude of the resulting cross product gives you. So in a sense, we kind of see that the dot product tells you how in line they are. One way you could think about the magnitude of the cross product, it's the area of a parallelogram that comes from both A and B. So if you have vector A, you have vector B. If you can imagine extending this, creating a parallelogram, this area is the magnitude of the cross product. Okay? And one other important thing to note, that if you cross two vectors that are the same, then that's just equal to 0 because sine of 0 is 0. Okay? So that is section 1.1, basic vector algebra. It's a little boring, but it's going to get fun soon, so it's worth talking about all this. Hopefully that helped, and if it did, please give me a thumbs up and subscribe.